All right, folks, so welcome. My name is Constantine Panis. I'm a professor from York University. Sorry. But it's my great pleasure to introduce my great friend Dima, who's a professor in computer vision at Bristol University. She's also a senior research scientist at Google DeepMind. And you probably have heard of her work in terms of egocentric vision. I mean, she has covered all bases and more. And you probably even worked with her data set. So she's created many data sets, including the Epic Kitchens data set, and more recently, Ego 4D. Yes. Right. So without further ado, Dima.
Thank you. Thanks for being here. Hopefully, I will tell you a little bit about what you can do with egocentric videos, and I'll start by telling you why does this matter. People who work in egocentric videos believe that currently we are in the era of a handheld device, right? I don't know how many of you are having your phones in your hand. I count when we walk in the streets, and usually it's between 60 and 80%, depending on the country and the busyness of the road. Everybody's having their phones in their hand. That percentage changes when it rains, then everybody holds their phones away. The phones are too important to be held if it's raining. But this is a nice illustration from the artist, Perez Casu, who tried to, like, these people are not in the same place at the same time. He just merged them over time, showcasing where we are at the moment. And of course, people are making fun jokes of where we are now with the handheld devices. The belief is once these wearable devices will come into play, because we apparently need to be connected all the time, we will be moving from this era to the era of the wearable device, right? So there are lots of competition of who will be able to deliver the most or the first usable wearable device. But the assumption there is once we do that, we will remain connected, we will have our hands free again, and hopefully we'll be able to return to being people who use both hands to do everything in our lives. And the question is, what can we do with the footage that will come out of these devices? Clearly, the cameras that we have in our handheld devices have proven very useful. Now, every time we take a picture when we want to keep a memory of what we want, what can we do with the footage out of these devices? From a more, say, scientific perspective, I'll be telling you about some of the tasks in computer vision that prove significantly harder when we test them in an ego setup, and some of the solutions or ideas that we've always wanted to work that also prove rewarding once we test them in an ego setup. So this is my personal experience, is that ego offers these two ideas, things become significantly harder, and some solutions become really worth pursuing. And I'll start by, I'll not present all of these, I'll present a few, but I'll start with something that's quite practical, which is domain generalization. Hopefully, I don't know how you're doing with lighting, but you can see the videos very well, hopefully. So this is a chef or a person cooking, cutting a carrot using the knife. This is a mechanic cutting a wire. Luckily, they're, smart enough that they chose a different tool. This is a construction worker also cutting using an angle grinder. And clearly, we all identify these three different actions with the word cut, because we're able to generalize beyond the scene, beyond the tools, into the notion that something is whole, and after the action, it becomes in two or more parts, right? So we can make this big generalization that we call all of these cuts. And the more scenarios you see in life, this is cutting using scissors in arts and crafts, or using a plier in gardening, and all of these are the words cut. And while this is generalizing across different scenarios, there are also interesting differences if we try to generalize across locations in the world. So this is cutting in Italy, this is cutting in India. And if you really look at the case, on the left, the knife is moving towards the fruit or the carrot, while on the right side, the knife is static, and the fruit is actually moving or crossing through the knife. It's an interesting discussion if you ask people why they're doing it this way, and they will tell you this is much cleaner because you don't need a chopping board, which we use mostly in the US, and that to them this is extremely unclean, and doing it this way is much safer from their perspective. So the question I wanted to ask is, can we generalize to these actions that we know, like cutting, opening, closing, across scenarios and locations? And this setup is built on top of the Ego 4D dataset, which is this huge data collection that was collected in 30 by 30 different universities. So we have Ego 4D, We looked through 13 locations, 10 scenarios, and we came up with these 60 action classes, things that we all know what they mean: lift, cut, open, put, close, take, throw, etc. We all know what this means, and we can, as humans, successfully generalize. The question is, can the models generalize? So we propose this 1.1 million samples. These are long-tailed, and everything you collect in egocentric setup tends to be long-tailed. There is a lot more of certain actions than others, but you can see that for each class, you have a distribution across the different scenarios. So if you want to do generalization, you typically need a training set for which your scenario isn't really there, and to test whether you actually can successfully generalize. So we take this distribution, we combine a contribution of a scenario and a location, say for example, cooking in Japan. The intersection between the two forms the test set, and then we remove everything related to that scenario and that location from the training set, right? So we chop the training set, getting every example that's collected in any cooking setting and anything that's in Japan. And now we want to test whether we can recognize cooking in Japan, generalizing across scenarios and locations. And this is one of 10 test sets. So this is the cooking in Japan, but we test 10 different combinations of scenarios and locations. The choice of these depends on the number of examples, because we want a decently sized test set. Good, so that's that setup. Domain generalization is such a cool problem, because the question is, can we really generalize to a new tool, to a new location, to a new scenario? And let's go through how we attempt to do that. So we take an example of, say, in this case, cutting in gardening setup, and we want to learn to generalize. Remember, when we're testing, we're not going to have any gardening examples. But during training, we have a mix of different scenarios that we'd like to generalize. So we take other videos in the support set, other videos in the batch. That's what we call the support set. And we aim to reconstruct this video. So we hide the video in the training, and we aim to reconstruct it in the feature space out of other videos in the batch. And we hope that this can represent something that looks like someone is cutting lemon, right? This is the training set here, but we try to do that across examples in the training set. And let's talk about what that means technically. So what we have is a video and a sentence describing the action. Then we have some frozen feature descriptions. We work with 1.1 million, so we can't really go back to we work in the feature space. But we want to learn these projections, F and G. That's what we want to learn. And hopefully, once I go through F, I would generalize. So I would have removed any knowledge of the scenario and the location. And we do that by taking this support set. So these are other videos in the batch. We project them in the same feature space. Then we look through this feature space to find similarities. We're hiding the diagonal. That means I cannot reconstruct the video from itself, but I can reconstruct it from other videos in the batch. So for every video, I'm actually reconstructing it as a combination of other videos in the batch. And I do that through all the videos in the batch. And then I match these to the text. So what I want a reconstruction that matches the text. And remember, the only thing here that's learned is F and G, right? So I am learning something that by the end, I can reconstruct it from other videos in the batch. And this is the open vocabulary setting. We also have a closed vocabulary setting, where we also ensure that this reconstruction can classify the action, right? So it should represent the video's description, cutting lemon, and it should classify the action cut. And after we've done this during training, that's it. During inference, there is no support set. We just go through F and hope that this now generalizes to a new scenario and setting. Let's look through what happens in training as an example. So this is a video from the training set, and this is being reconstructed by combining these 5 videos. So we hide this, and the combination of these 5 videos achieves a representation in the feature space of that hidden video. Good. So this.
When you say it reconstructs it, you mean there is some loss?
A linear combination of the representations of these videos.
In pixel space.
In feature space.
Feature space.
In feature space. So, okay, The results are decent. So this is standard cross entropy. And as you can see, it's a very, very hard task. So without generalization, we are on 23%, right? So this is the standard ability to generalize. I'm showing here 2 of our test sets and the mean of all 10 test sets that I showed you. These are the number of methods that have proven useful for generalization in images. So you have Coral and MMD, which are representation based, and we have more recent ones like mix-ups and do prompt. If you're into this area, you might have heard about these ideas, but this is our reconstruction method on the best set, the worst set, and the combination. So we're getting a good additional margin, but even at its best, we're not exceeding 28% accuracy on this very, very hard test set. So if you're interested, you can look more details into this paper. I introduced it as one of these cases where it's a natural setup. Can we do it? Domain generalization works. And that's one of these things that proved useful when we go into. So domain generalization currently, if you know it, is dying a little bit. Everybody says we don't need domain generalization. We can just generalize in all examples of the world. And in this setting, we really show that you can't generalize even if you have a million examples and you need to achieve some level of domain generalization. Okay, the next topic that I really, really like is audiovisual. And you know, one of the things that we worked on for a number of years, big credit here to Jason and Jacob, who led this work. They worked on this for more than a year, which was presented like ICASP. And let me tell you a little bit about audiovisual. Usually, videos come with an audio stream, fantastic. And we have for years used this knowledge of these 2 modalities. We label the video. So we say the person is doing these examples. We usually label them with the start and end times and with an action description. Wash carrot, wash tomato, take knife, cut tomato. And then we've been feeding these audio and visual data to models. And the conclusion in multimodality is you get 2-3%, and that's it. Even at best, additional modalities are not giving you this huge boost that you think they should be able to do. We base this work on the assumption that there is something wrong in this setup. For example, you will never be able from audio to recognize whether someone is washing a carrot or a tomato. Feeding the audio into a network with those labels as output is, you know, in principle, you're asking audio to do an impossible mission. We know that some actions are silent. So if you take something, you can't hear anything in the audio stream. And, you know, what's the solution? So we went through the exercise of labeling only the audio stream. So the annotators only heard the audio, and they were asked to label the start and end time of the audio event and provide a semantic description of what they think they have heard. So for example, in the case of washing, the only thing they know that there is a tap running. In the case of cutting, you really know that someone is cutting some level of food, but you don't know what exactly it is.
Was this a closed action world, or they were just?
It's completely open vocabulary. But for the first time, we have a data set for which it has been labeled for visual actions. It has been labeled for audio actions, and we can look at these. And it's very interesting because for a while we've had these visual actions on the left. So we have 90,000 actions visually. Now we have 79 audio actions. These are labeled into 44 classes. So we take the open vocabulary and we group it. But also we have 39,000 audio events where the human hears something, but they can't give it a semantic label. So the 79, the human knows what it is. There are other things where some crackling is happening, but you can't give it a confident audio label. For now, we haven't worked with these, even though they're released, but we've worked with these. But the data has been released under EPIC. So after we put it out, we tried to figure out what can we do with this work. And this is a work we presented this CVPR. We call it the time interval machine. So for the first time, we aim to learn from these 2 sets of labels. Remember, multimodality typically expects multiple input, 1 set of labels as output, right? And here we have 2 sets of labels as outputs. We're saying in visual, you have different labels, different start and end times than if you're looking as audio. And we wanted one network, one method to use both sets of labels. So yeah, transformers it is, of course. That's the current era. So you take a video in that takes both the visual and the auditory stream, and we want to put it into a transformer. The only trick here is how you query this transformer. So if you want to ask about some visual label, then you want to feed a start and an end time and some signal that says this is a visual class. You put these three into an MLP, and that gives you this question. So you're asking about this interval in this modality, and the output will be a visual label. The same transformer will take a different start and end time and a plug that says this is an audio class, and it's supposed to give you that I hear now an audio class. So we want to put all these together, whether a person is rinsing a sponge or you're heating water, but all of them are being put into exactly the same network. And that's it. With a little bit of engineering, this is the network. So you have audio and video. Again, you have frozen encoders. We're a university after all. We can't work with non-features. But these are your projected features. We also have these queries, which are start and end times and labels. We put them through what we call a time interval, MLP. The distinction between this and your standard positional encoding is here we're encoding intervals, not one positional embedding, right? So this gives you these positional representations. And now we have a token, a CLS token that we use to query. And then we also put our feature durations into the same MLP to give you a representation of your features. So the same MLP can take visual queries and can say, for example, 0 to 1 is your first feature, 1 to 2 is your second feature. So you also encode the features in the same space. The only thing left is a modality encoding. So you know which features are visual, which features are audio, and it's a vanilla transformer. And the output is either a visual class or a label or an audio class. Why we like this work is not only because it's proven the value of these two different representations, but because we are able to outperform methods that use LLMs. So here we're not using any knowledge of an LLM because LLMs help, right? If you're opening water, you're washing. After opening, there is closing. So LLMs have proven useful to train for action recognition. But here, without an LLM, we are able to outperform other methods that use significantly bigger backbones in the visual space as well as in the visual and audio modality. We tested this on Epic Kitchens, which is one of the datasets that has 2 labels of modalities. There are a few others. One is called the perception test, which also has visual and sound labels. Before I leave this work, I like this representation because this is the output of I told you there is this time interval MLP. We just take the output of this MLP and we do TSNE over it. And we can see for the 3 data sets that the network is learning the 3 different dimensions of the interval. So it's learning the duration of the interval across 1 dimension, the start time of the interval across 1 dimension, and the end time of the interval across the 3rd dimension. So the 3 dimensions of the interval are encoded in different shaped TSNEs across different data sets. So this is showing the value of encoding not only positional embeddings 1, 2, 3, but encoding interval. Okay, before I move from these 2 topics into 3D, I can pause for questions. Okay, otherwise, we're going to lift ourselves from 2D to 3D and do a little bit of 3D understanding. So through a successful collaboration with Oxford and Neighbor Labs, we basically took our Epic Kitchens videos. So these are videos, what happened? Okay. These are videos that we have collected as is many years. Okay, so these are the videos we collected many years ago. Something is odd in maybe the connection. Let's try again. So these are the videos, and we're basically lifting them to 3D. So we have not collected the data with 3D in mind. We're taking the videos as they are, and we are lifting them to 3D. Somehow this video isn't playing nicely, but I'll just go through it. So you can see the person on the left. What is different between these videos and standard videos for 3D is there are lots of dynamic objects here, right? There are hands and there are lots of things moving. So if you ask someone who's doing 3D or call map, can we lift this to 3D? The answer is typically no. And we did this through some number of tricks, particularly sampling the right number of frames from this video. For example, when the person moves around, so you see this motion, we sample this at 60 FPS to be able to reconstruct the scene correctly. Without doing that, if you even go to 30 FPS, you can't do it. If you put this into standard call map, you can't do it. But we started lifting these videos into 3D, and perhaps just to show you what we can do with this, so we can now put some of the hands in 3D, so cool. We can also do some novel view synthesis of dynamic scenes. So there's a fixed camera now. Again, the video doesn't have a third camera. It wasn't collected with 3D in mind, but we can now do some dynamic novel view synthesis. Cool. So, good. Now we have 3D representations of the scenes. I would like to put objects in it. So I would like objects now to start moving in the scene, again from these videos. So this is a work that will be presented in 3DV next year, and it's called Out of Sight, Not Out of Mind. It's a little bit of a strange visualization, so I'll explain. This is basically the static world. So this is the call map we've lifted, and it's currently with some texture. So this is the map of the static world. This is the egocentric video. This is a view of the static world from where the camera is, but it's static. What we're adding are these colored dots. These colored dots are all objects that are moving in the scene. We want to put them correctly in the scene and track them in 3D. Okay, let's hope that this one will work. Okay, so you can see an object being moved. It creates a dot in space, and that dot is being tracked. You can see it in view, but you can see it in the standard scene, and the object is now moving in the scene and being placed in the new location. We don't know what these objects are. If you hear about some of the 3D current approaches, they usually assume it's people moving. Here, we don't know what these objects are. We're not giving them semantics. We're just moving them in 3D. So we started labeling some of the data in 3D and lifting these objects to 3D. Again, none of these videos were collected with 3D in mind. We just gave people cameras to collect data. So how do we do that? Okay, first, we have labeled masks of objects. This is manual labeling. We use something called visor, which are manual labels of objects in the scene. You can do that with SAM with less levels of success. But we wanted to remove the problem with the masking for now, so we're using ground truth masks. We put this into molecular depth estimation. So this is a depth estimation of only a single dynamic view. So that has both the static scene and the dynamic objects. However, even with what people call metric depth, these usually don't work very well. But we have a knowledge of the scene, so we know where this is in view. We can use some knowledge of exact locations in the static scene to map this depth to metric depth. Right? So we know where this is in the scene. Great. The only thing we're doing now is to lift these masks. Currently, we're lifting the center of the mask, so we're not really representing a big object, just its center. That's why you've been seeing these dots. And we can now lift these to 3D. How well does this work? We don't have any 3D ground truth, but we can start looking at some examples where I see the same object from different views, and this object is static, and measure the error we have. So by doing this, we can showcase that our error is between 0 and 5 centimeters. If you are into action understanding, this is great. If you're in pixel perfect 3D reconstruction, this is horrible. So it depends which viewpoint you're coming from. But that's what we're doing. We're lifting the object in 3D. Now, if you put an object down, you go, you leave, and you come back, we want to keep tracking it. So we need to match. And here we use a combination of appearance and 3D location. Because if you've lifted there and coming back, that's probably the same spoon or the same cup. And we just need to keep it in space as you come back. This is allowing us for the first time in egocentric vision to say things like, is this object in view or out of view? Also, is this object in view but occluded? Because I'm looking where I think it is, but I can't see it. So it's somewhere in my direction. I don't need to turn to find it. And is this within reach but out of my field of view? Is it within my periphery? Can I stretch my hand and find it, or is it currently in my view? I really like this work. This is a collaboration with Andrew Kanazawa and people in Berkeley. It took us 3 rounds to get it accepted. And the main reason is people wanted 3D ground truth. These videos were not collected with 3D in mind, so we don't exactly have 3D ground truth. So having been frustrated, and this is usually what happens if you want to collect more data, is you're showing people an interesting problem and they keep telling you, where is the 3D ground truth? So for the past year and something, a large number of people in the team have been collaborating to collect for the first time a data set that is also in the wild, so in people's homes, but comes with 3D ground truth. This is not yet out there, so you're one of the first people to hear about it. Hopefully the data will be out for the end of the year. But this is a large collaboration between Bristol and also some of the people who were at Bristol and now in other universities. We came back to collect an update on Epic Kitchens. So what we do here is, again, similar to how we've done before, we ask participants to come to the lab and we offer them this nice backpack, which when they go home, they can unpack it and find inside it a number of ARIA devices. ARIA comes with really interesting 3D understanding IMUs, and this is a collaboration. This was funded by the ARIA team. So we give them 4 devices because while these devices are great, their storage is very small and their battery is tiny. We give them a power bank so they can remain connected to the power bank, and a phone with things set up. We also give them a digital scale, and I'll tell you why later, and some recording instructions. And the only thing we tell them is, please wear the device before you walk into the kitchen, and don't stop recording until you walk out. And please record everything you're doing in your kitchen for 3 days. So these are chunks of data that people have done in their home. We don't tell them anything about what they should do. This is their kitchen. So they're just doing exactly what they would do for these 3 days. And this, to me, is key, because once you don't do that, once you give people instructions, can you cook omelets? Then the whole thing becomes so fake, in my opinion. Well, maybe I'm a bit extreme in my belief in the need for unscripted data. So I'll tell you a little bit about how we label it and then show you a few examples. So these are the videos. And we ask the people after recording to take whatever they have done, what they've cooked, and to give us a corresponding recipe online of what they have cooked, the closest recipe to what they have prepared. So again, this is after the effect. Sure, you've cooked something. Can you look online into something that looks similar? Also, can you tell us what you've changed in that recipe? So we have an online recipe, we have the modified recipe, and we have the video. Great. Then we go and associate those steps in the recipe with where in the video they are. And of course, these are like very tiny steps. You do millions of things to achieve one recipe. So for the first time, we're also labeling what we call prep. So what did you have to do to achieve that step? Imagine, for example, you wanted to wash something, you needed to pick it from somewhere, you need to get a bowl. So all the related actions are also labeled with start and end times. And we've given them these digital scales so they can collect ingredient nutrition for everything they've cooked. So they have weighed these ingredients in camera, and we know exactly when they added them to the recipe. So that's one level of knowledge that we've collected with our data. Remember, we want to lift everything to 3D. So I'm just telling you now about the 2D labels. Then we have the fine-grained understanding. So these are descriptions of the actions they've done. So every single action is described and labeled with a start and end time. And also we parse these descriptions of the actions into verbs, nouns, what hands they use, how they've done the action, and why they've done it. So these narrations are significantly more detailed than what you've seen if you've used Epic or Ego for it. And since we love audio, we also label the audio events similar to what we've done with Epic Kitchens. The final level is we also want to track objects in 3D. So first, we label the objects in 2D. Every time an object is moved, we label the start of the motion, the end of the motion, and 2 masks corresponding to the object before moving and after moving. And we do that for every object that moves in the space, small or big. And these are manual masks on top of these bounding boxes of objects that are moving. So these are the 3 levels of knowledge, and now we want to lift them to 3D. Remember, we don't have any knowledge of people's kitchens. We just gave them a backpack and they came back with footage. So what we do is we work with an artist who builds a blender representation of people's kitchens. That is after the effect. So that artist goes and labels every fixture, every cupboard, every drawer, every sink, every hob for the full kitchen. That allows us now to lift our objects into 3D and associate them with the fixtures they come from. So these are some of the representations of objects that now have 3D ground truth. And again, depending on where these objects are moving, some move very far, some move very close. Okay, I don't know what do I have next. Okay. And one of my new favorite hobbies is to understand how gaze impacts object motion. So because area comes with gaze, we also know, remember we've labeled the objects and we've lifted them to 3D. We can look at when you look at the object before picking it up. So we can give you the knowledge of when people prime the object before lifting it up. And also when you prime the location before putting it down. So we have the gaze information. You look, you pick, you look, you put down. And this is labeled for all object movements. So that's what we have. Let me show you some of the footage. So this is the level of narrations that we have. Again, if you've seen narrations from Epic Kitchens before, you will see that these are quite more detailed than they used to be. We paid these participants well. But this is the level of density that you're getting. And again, they're describing every action and also why they are doing it and how they're doing it. Okay, this is some of the audio. I was told you're not going to hear the audio here, but at least you can see the types of audio events that have been labeled. And these are some of the 3D annotations. So you can see that every time you open an object, this is the gaze. So we can see when the person looks at the object before lifting it. We also show here how when the cupboard is open and when you're picking this cupboard, and this is the priming the location of put down. So this is knowing that you've now looked at where you're gonna put it, and now you're gonna go and put that object down. Yes.
So how do you do the registration from the Ego video data to the blender?
So this is using ARIA. That means the data has RGB and SLAM and IMUs. So we're lifting that through the MPS.
So you're sort of registering that.
Yeah. So we have a point cloud. On top of the point cloud, we're building the digital twins. I don't know what this. Oh, okay. These are just more kitchens with the. This is sped up, so you can see. So every time you see a dot, you see an object being picked up, and you see where that object is being placed down, and you can see the corresponding fixture. I am always grateful because I come up with these crazy ideas, and the students come on board. It's really like, given all the data sets I've done, this probably drove us to madness the most. Well, we're very happy that at least now no one will tell us you don't have 3D ground truth, and we can go back to doing stuff. And as usual, now you want to showcase that your data is useful, led particularly by Hazel Doughty, who led this VQA setup. We also took all these annotations and created a VQA. So we can ask LLMs, can they solve this problem? Do you know what happens in the setup? So this is the type of narrations we have, and these are types of questions that we've created. And we were hoping that LLMs don't do well, and indeed they don't. So we've tested open source ones like Videolama 2, LongVA, and we've also tested closed source one. Gemini Pro tends to be the best in long context. And again, you can see that at best in our setup, Gemini Pro does 37%. Different to standard VQA, our negatives are not LLM created. Our negatives are examples from our annotations. So for example, if someone picked a spoon, when we ask, where did you put this down? Our negatives are other examples of where spoons have been put down in this kitchen. I think is one of the main reasons why this is not as trivial. Some of the VQA, for example, we ask, what is the best description of how the person did this action? Pick up bowl of coconut milk. And again, all these 5 descriptions come from people's narrating examples of picking up stuff. And you can see the one that is the ground truth labeled in green, and you can see the response of models. So Gemini is this purple one, and you can see other models, currently failing. And when people say the only problem with LLMs is long term, this is one of the examples where this is fine-grained, short-term, and models don't do well. So LLMs can't really solve even short action descriptions at this level. This is another example of how many times did you open this, which in this case is labeled by a bounding box in an image. And this has been opened 3 times, and models can't get this right, but that's how we know they can't count well. And this is how much the person weigh in this video. And again, clearly you can read the number here if you know what that means. And models cannot really successfully do that. We have 26,000 questions, but we think if you just take our annotations and our method, you can get up to 100,000 questions, because again, the questions come from the annotations. Hopefully, this will encourage more people to do stuff with 3D and with 3D data. Before I conclude, I don't know where we are with time. I took maybe a bit longer. There is a paper we wrote out called An Outlook into the Future of Egocentric Vision. It's an easy read, because what we've done is that we just imagined what the future would look like. We wrote stories about what people will in the future do with ego vision. We worked with a great artist who drew these stories. So you can imagine someone going home, Ego AI, which is our future, will tell you exactly what you need to eat today based on all the ingredients you've eaten and what's in your fridge, because it knows everything. And then it will guide you through the exercise. You might have a 3D projection of Remy from the Ratatouille movie taking you through the exercise, and then you can get reminders of things, recipes of how to improve your cooking. I need that. And then, lots of examples about what you can do in the future, including how you can engage with other people wearing similar devices. This is the future as we imagined it. I presented this with mixed reactions. Andrea Vidaldi told me that this is not the future he wants. So, I apologize if that's not the future you think it is. And after we wrote these stories, we mapped them into our tasks, showcasing the gap between the two. So you can read this as just stories, or you can read this as a nice survey with the seminal work and the gap between the current examples and the future. So if you're interested in more ego, this is the right paper to look at. And I get the credit always to come and present these fantastic works, but this is the work of a great team. I'm really grateful. Everybody here works in ego all the time, and everybody here was involved in collecting this great data set, which we now called HD Epic, so highly detailed epic. And we hope we'll bring even more people into the area. Thank you very much.
Have time for questions. Are there any questions?
Yes.
Did you check how humans would do on those VQA questions?
Very well.
I don't even know.
Yeah, very well. Of course, it's
Dima,
very.
could you repeat the question just
The question is, do we know how humans do on these videos? They do very well. We couldn't check all the 26,000 questions, but people are more than 90%. The problem is that some of them is like, how many times did you watch? You really need to watch the video in full. So supposedly, methods should do better because they have access to offline data than a human watching once. But clearly, they currently not yet. They can't do that.
Did the LLMs fill on all sorts of questions, or are there particular questions where they were actually good at?
They were better in certain things than others, in guessing certain things about recipes. They can guess things really well about recipes, so they're doing well with recipe description. That is, where is the step? When did you do this step on a particular recipe? Gemini in particular does well, but yeah, and they do worse in understanding this 3D motion.
But when I look at this plot, it's like they're all worse than like 70%, or all of these. Are there not tasks where it's like 90% good? Like
No, none of them does 90%.
For all the videos.
For all the videos. No. We were not. Yeah, this 53% was surprising. We didn't again. This is very different to standard VQA because the negatives don't come from LLMs, and that typically is what most VQAs are at the moment. So you're asking LLMs, what would you not like as negatives, and then you're asking them again. So there is a bit of a loophole in most VQAs. Yes.
Yeah, the data set's like super impressive. was just curious, like some of the videos were like, when you open the fridge, it was almost like green or bluish casted. And I wonder if like humans kind of can, depending on the lighting, remove the, like, for example, in this one,
Yep.
like, I know that's a white fridge, but, and I imagine for a machine, for an algorithm, it's going to be quite challenging to deal with this. And so I just wonder, like, what do you guys think about this?
Yeah, so we also, when I first saw the footage compared to Epic Kitchens, I told the area people, sorry, the question is there's a bit of bluish background. This is a cheaper sensor, visual RGB sensor, than your GoPro. So what typically happens is that this is the typical sensor, but GoPro does onboard color fixing,
Right.
and so you like that setup more.
Right.
But the data input itself is the same. Of course, one of the questions is this impacting data? And in the paper, we compare action recognition methods on data trained on Epic, and it's doing fine. So models don't seem to be as impacted, but I appreciate that there is an element of visual likeness that I like, oh, Epic looks more colored. But apparently, and I am not an expert in sensors, people here are better than me, they tell me that this is a post-processing improvement.
Yeah, I guess to me it seems like one simple thing that could make these models better is training like a pipeline, like a image pipeline that processes specifically for your task or whatever. So if you have like
I genuinely doubt that this is the problem, but
maybe I don't know. Perhaps,
I'm happy to be correct.
Like this is data set is amazing. And you have like incredibly fine-grained labels for like across time and space in 3D.
On the left.
So if you want to learn good representations that are that fine-grained, what sort of directions, like supervised, unsupervised, where do you see kind of like
good question? Good question. I think realistically, there is no single task that can learn good representation. So we're either in the phase of multitask supervised or unsupervised. I don't see multitask supervised working.
You're going to have to make some more data sets.
Exactly. So realistically, at least the data knowledge has to be unsupervised to a good amount. Now, what is the way? Do things have to be in 3D space? Do we need to lift everything from 2D to 3D? This is my current bet. Is that really videos are partial representations of the world, and only operating within the video stream sounds completely crazy in these setups. Now, is there anything that represents a latent 3D representation from video? Not yet. But again, I have no answers. I typically am good at creating problems. And someone else will solve them, will find interesting solutions.
If Aria gives you point clouds,
yes,
what's the need for the digital twin?
Because the point cloud doesn't tell you anything about moving objects and where they are in space. And also, we can't answer questions like, where did I pick this from? So knowing where things are in the space require an understanding of basically the scene, right? So we want to ground all these actions in meaningful locations in space as opposed to a point in 3D.
Couldn't you do that with like the registered point cloud rather than render?
I will give you then just a 3D representation of every point, right? But I will not be able to ask questions like how many times they opened this cupboard, or questions like what happened to this object? Oh, I picked it from the drawer and I put it in the dishwasher. These semantics will never be available in the point cloud. Of course, the point cloud gives us a starting point.
Sure. So how much effort did it take to actually label it?
X times more than I thought it would.
Who did the labeling?
Who did the labeling? So it depends what you're asking. For example, we had an artist that works with us to create the Blender scene. We had the manual masks were by a set of 5 annotators that we worked with in Visor before. They're dedicated annotators. The description, the high level description, were the participants themselves. So each participant worked with us between 50 and 100 hours, between the data collection, giving us the recipes, giving us the detailed descriptions. I'm pretty sure, while we paid them well, I'm pretty sure they regretted coming on board. So it depends. We really wanted the participants to tell us what they did and why they did it. That could not have been done by someone else. Every interface you see here has been created by us, tested by us before being given to annotators. And we've worked with annotators we know as opposed to Mechanical Turk.
So one more question. This is all within the kitchen,
Yes.
which is a small fraction of.
I always think if you want to talk about tool usage, how people use tools to achieve tasks, kitchen is the hardest setup. And my bet is once kitchen is solved, everything else is. I can't see that. Now, there are other aspects of life like social interactions, navigation of scenes that you don't see here. But this is out of my interest. I am very interested in hand-object tool interaction. That's why my bet is kitchen-based. There is an aspect, of course, that when you ask people to collect data at home, and you tell them, can you collect data in your kitchen, they're a lot more amenable than if you tell them, can you collect all through your home? Because you are always in the kitchen for a purpose. You're not there just to chat. So our setup over the years has been, we really can collect very interesting footage. And we have different levels of skill in humans, and everybody can collect data in kitchen. So that's an aspect, but it's not the only reason. The real reason is hand tool object usage in the kitchen is definitely the hardest in our daily life. And for me, if this is solved, I don't see what else remains challenging. Social, of course, is another aspect, is out of my research interests.
Okay. With the ego vision, like, I mean, I guess in a sense you're trying to get the perspective of like the person wearing the device.
Yes.
But I guess in reality, human vision is kind of hard, right? Like you have like foveation, like you focus on certain parts of the region you have, and then like sometimes there's things out of your field of view. Your eyes don't actually see it, but then you like in your head you have like a model of where things are. Do cameras like I guess you have like one camera here that has like some field of view.
There are 3 cameras. So there are 2 SLAM cameras and 1 RGB camera. That's what ARIA collects. Field of view is fairly big. Haptics, of course not. And I really look forward to sensors. The moment there is a haptic sensor that I can use with water, I am up for collecting haptics, but that does not exist. So, of course, we're not getting the touch, right? But in terms of the field of view, I think we're very close to the human's field of view. In terms of saccades and fixations, there is a big question of whether we need more detail to understand this level.
So you have a pretty good sense of where the person is actually looking.
Absolutely.
All right, we've got time for, let's say, 3 more questions over here.
So my question was about coming back to the fact that the participants were collecting their own, let's say, description of the recipe.
Yes.
Is there a bias associated to the type of language that they use based on their native language, their competence in English, or even like their cultural differences in the way they describe the recipes that could potentially, like, be a bias in the model?
Yes. So when we collected Epic Kitchen's first version, we collected with people's native languages, and we released the data with people's native languages, and no one used it. Everybody used the English translation. So in this setup, we used only worked with people whom either the English is their native language, or they have been in English-speaking countries long enough that we are confident about their description. So indeed, we excluded lots of people we could have collected from for that purpose. I would have loved to work with a linguist who is interested in understanding this type of bias, but absolutely beyond my expertise.
So this data is incredibly rich, like super impressive.
Yes.
And when you started talking about gaze and where they're priming and what's their next, the thing that straight come to my mind is you can add EEG signals into the mix, and you can start trying to predict where the person is thinking about doing.
Yeah, absolutely.
Board has enough with this.
Do you have a way to? So gaze has always been something we were interested in, and there were no gaze devices we could give to people at home, right? So the previous gaze sensors were 30, 40,000. I would never send them with someone home, right? So So this was a huge jump. Indeed, there are interesting sensors. I know nothing about EEG. The claim is indeed they can read what we can think. I have only seen them in cases where people are looking at images.
Yeah.
So would I buy into they will read my mind and figure out what object I'm picking next? I don't know. I don't know. Every time we collect data, I tell the students, this is the last time we're collecting everything we need. That's the last. I've done this 4 times, and this time I'm not saying this is the last time. But hopefully this will serve us for a number of years. And maybe at least until the number of students graduate. And because if I tell them now, let's collect more data, they will just resign.
All right, and just last question over here, and I think
So yeah, thanks for the great talk. Some of the works, it seems like the techniques you can apply to any video data set, such as the audio and the one in the domain transfer.
Yeah.
I just wonder, in your opinion, in your view, what do you think the biggest thing that egocentric these data sets bring to the table? And also when you approach developing a method to operate on these data sets, what are your primary considerations?
Yeah. So the word video means lots of things at the moment. If you download a paper that claims to do video understanding, some of them are taking movies. Movies are shots are well defined. People have a script, right? So there is movies, and then there is here where there isn't even shots. Like there's no end to a shot, right? And in between comes everything. Comes what's in your YouTube, comes vlogs. So there is like a scope of what a video is. What differs in that scope are 2 dimensions. One is this edited or not? Are you getting the raw footage or has it been edited? And 2, why is this person capturing this? Are they capturing a story? Are they following a player? Are they, is it a wearable device? And we have a very poor understanding of how can we bring these 2 dimensions onto a common method. So I am yet to see someone claiming that they operate across all this spectrum. And this is one of the problems. We don't have enough people working in video. Anyone who's working on images and wants to help, we are in need of every individual. So this is one aspect of video understanding. I like it because it's unscripted. And I like the fact that I don't need to worry about faces. And it's clearly, we know what's happening here. Humans can do it and machines can't. So that's the challenge I've put myself to solve. But this is of no use if you want to understand stories in movie characters. And both are video understanding.
Thank you.
all right. So let's thank Dima again.